Okay, in this next video, I am going to be recording my screen and showing you guys the JMP software that we've looked at in class to kind of give you a better idea of what I'm talking about with this sampling distribution or how sample proportions vary from sample to sample. So I want you to kind of keep thinking about what that means. So what I have set up here is a simulation, and this is basically like flipping a coin, okay? I got a 50% probability of flipping tails. So this is literally simulating flipping a coin. All right, so what I'm going to do is flip this coin 50 times. All right, so let's go ahead and do that. We're going to do one sample right there, and there it is. Okay, so I've flipped the coin 50 times. Now what I got here is the distribution of the sample. This was my one sample of 50. I got 23 tails and 27 heads. So this is 23 and this is 27. And if you examine the counts, 23 out of 50 tails, that's binomial, 23. But if you instead look at the proportion, that's 46%. So in this particular sample of 50, we had 46% tails. Now we all know that it's supposed to be 50%, but like we talked about with Randy's simulation and just data in life in general, data is not black and white. Even though it's supposed to be 50%, we didn't get exactly 50%. We got 46. So here is one sample proportion. We're going to make a histogram. Here's one bar for the histogram. All right, now I'm going to do another one, another single sample. Draw a sample. You'll notice a couple things change. Okay, so here's the second sample. This time we had 30 tails, so we had 60%. There's that sample proportion in our histogram. Now down here, it's calculating an average of these two samples. So right in the middle at 53. So notice neither original samples got us to 50%, but the average of them is getting closer to 50%. Let's draw another one. This sample had 52% tails, right there. The average, 53%. So what I'm going to do is I'm going to keep drawing samples. That one had another 52%. So that 52% got peaked taller because it was 2 as opposed to 1. These each had one sample. These were 2 samples. So there's another 52% and 58%. And 52%, and 54%, and 50%. There's our first one that actually was the population proportion. But the cool thing about this is we actually technically are supposed to draw infinite number of samples, or every possible sample we could possibly draw. So I could sit here and just keep clicking this draw additional sample button, where I'm just getting more and more samples. So far I've gotten 25, and you could see how the proportions were changing. Notice that average of the proportions is getting closer and closer to 50%. But right here I can tell it to do a whole lot more than one. So I could tell it to do, say, 100 at a time. So I'm going to take animation off, because if I animate it, you got to go through each one. So I'm going to take that off so that it just, boom, does them all right away. So notice right now we're at 25. I'm going to press this button, and now I'm at, boom, 125. And notice the mean. This here is the 60%. That was my last sample. The 100th sample was at 60%. I don't see all the other ones. The mean is getting closer and closer to 50, the true population proportion. The shape is getting more unimodal and symmetric. I could do another 100, and another 100, and another 100. I can even make this be 10,000 and do a whole bunch of them at one time. And notice this shape is becoming more and more like the normal model. The mean is fairly close to 50%, and the standard deviation is at 0.07. So if I go to my calculator and I type in the square root of 0.5, that's P, 0.5, times 0.5, which would be Q, divided by 50, my sample size, that's that formula for the standard deviation. I get on my calculator screen 0.0707, which is pretty close to what this standard deviation is. So it's through simulation that they discovered all these properties, that when you examine sample proportions, as you look at every possible sample there is, we get a bunch of sample proportions. It makes a histogram. That histogram turns out to be normal if the conditions are met. We haven't gotten to that yet. Centered at the true population proportion of 50%. You can see I'm pretty darn close to that right now, with a standard deviation of square root of PQ over N. Now what this does is it kind of tells me if I were to get a sample proportion of 0.8, I would be like, no, that's really kind of unusual. And even these guys right here, this is 0.7. Even out here, there's a 1 or 2 samples that ended up at 0.7, but it's rare. It's not something that should occur. And down here at, say, 0.3. We do expect 50. We're not going to be like maybe completely shocked by 60 and 40, but we can start measuring our z-scores and start figuring out what would be an unusual sample proportion. So what this is called a sampling distribution for the proportion. This is what we expect sample proportions to look like. It's how much we expect sample proportions to vary from sample to sample. We expect them to be near 50%. We do know there can be some variation. We can start to quantify what would be too much variation, what would be unusual. I can change this to something other than 50% if we want to start over. Maybe start this at, say, 20%. I'm going to go ahead and increase my sample size. We'll go ahead and just do 10,000 right away. Notice it's still roughly unimodal and symmetric, centered at 20%. And if we do our square root of 0.2 times 0.8 over 100, we would get that standard deviation.